Hey guys, Jake here, coming at you with another math problem today. Today I'm going to be showing you how to solve this problem here. We're going to solve the separable differential equation dz dt plus e to the t plus z equals 0. I wanted to show you how to do this problem because this is one of the problems on my Calculus 2 study guide or integral calculus cheat sheet that I came out with recently. There's a link down in the description where you can check that out. You can go grab yourself a copy of that right now. Should make studying for tests, doing homework in an integral calculus class way easier for you. So go check that out in the description or in the pinned comment below. And please, if you find this video helpful, be sure to hit that like button down below, subscribe to my channel, hit that bell icon. That helps YouTube put this video in front of more people so that, we can help more people do well in their calculus class. So let's, help as many people as we can together. But anyway, let's go ahead and jump into this problem. So as the kind of title of the problem or the type of problem suggests, with a separable differential equation, typically you want to start these kinds of problems by separating your variables. That's, kind of the idea here. And that's exactly what the formula on my Calculus 2 study guide suggests, is basically we want to get, obviously in this case we have z and t instead of x and y, but regardless of what the variables are, you still want to get things separated. So basically our goal here is going to be to get our z and our dz on one side of our equation, and then our dt and our t on the other side of our equation. So this is kind of a weird one because, basically everything, our dz, dt, t, and z, they're all on the left side of our equation. There's nothing on the right side. And as a result of that, this problem is going to start a little bit different, maybe a little bit weird compared to a lot of these other separable differential equation problems. But what we want to go ahead and do, first of all, is basically just start with moving this e to the t plus z over to the other side of the equation by just, simply subtracting it from both sides. And basically what that's going to do, that should be a plus. Obviously, if we subtract it from the left side, this is just going to cancel, and we're just going to be left with dz dt equals negative e to the t plus z. So the reason why this is helpful is you want to kind of keep in mind the formula in my study guide that I was talking about. It basically says that what we want to do is get our separable differential equation into a form where we have, dz dt in this case. On my study guide it's x and y, but like I said, it really doesn't matter what variables you're using, it's the same idea. And we want to write that as some function of z times some function of t. So basically our goal here is to think about how we can split this up to write it as something with z times something with t, have them be, completely separated and just being multiplied together. Well, what you want to keep in mind is when you have an exponent, like we do here, you can combine two different exponents with the same base by adding their powers. Similarly, you can do the exact opposite. You can break apart an exponent with the power of the exponent, this t plus z being the power, by splitting that into two different exponents with the same base, where the power of each of those exponents with base e is whatever each of these pieces are. So basically what we can do is we can rewrite this as e to the t times e to the z. Of course, we would want to keep our negative sign out there. It doesn't really matter which piece you're putting that negative sign on, because a negative e to the t is the same as, negative e to the t times e to the z is the same as e to the t times negative e to the z. It doesn't really make a difference. It's going to end up working out the same either way. The important piece is that now we have this function of t here being multiplied by this function of z, just like this formula over here from my study guide suggests that we need to do. So what that means now is we can move our dt over to this side of our equation, move this piece with the z over to the other side of our equation, and then we'll be able to, basically integrate both sides from there. So if we multiply the dt over and then divide the e to the z over, we're going to get 1 over e to the z times dz equals negative e to the t times dt. Okay, we just had to multiply both sides by dt, that would cancel it over here. Divide both sides by e to the z, it would cancel it on this side and move it over to that side. So now what we can do is we can throw on an integral sign to both sides of our equation, and we can just integrate both of these equations separately. So the reason why this is nice is because now we have this function on the left side of our equation, 1 over e to the z, which we're integrating with respect to z. And then on the right side, we only have t's over here, and we're integrating with respect to t because we have our dt. So basically, once you get everything separated, you just integrate both sides. Before we integrate this left side, though, what you want to do is rewrite this. We don't really want the 1 over e to the z. That fraction makes it kind of difficult. So what we can actually do is rewrite this as e to the negative z power. Because if you make the power negative, you can, flip a fraction basically. So in this case, it's on the denominator. We can bring it up into the numerator by making the power negative. So these are going to be the same. Then we're still going to have on the right side the integral of negative e to the t with respect to t. So now we can just integrate both of these functions. The integral of e to the negative z with respect to z, you could do that using U-Substitution. If you want to check out, I have made a video on how to do that. Just click up there at the top of your screen. That'll take you to a video about that. But if we do apply U-Substitution here, that would show us that the integral of this is going to be negative e to the negative z. And then over here, we're going to get negative e to the t. And that's just because the integral of e to the t with respect to t is just e to the t. Putting that negative sign in front, it's just going to carry through. So we're going to get negative e to the t over there. And then since, looking back at the very original problem, we had dz dt. So what that tells us is the letter that's on the numerator here, the z, that's going to be the function, and then the letter on the bottom is our variable. So z is a function of t, which means when we're trying to solve this separable differential equation, what we want to do is get z on one side of the equation that we're solving for, and then some function of t on the other side. So basically, that means that we want to get the z by itself, which means we're going to move, everything that we can over to this side of the equation over here. So when we put our plus c, we can just put it on this side. We don't have to do both sides. Now what we want to do is solve for z. So we're just going to algebraically manipulate this to get z all by itself. So first of all, we can multiply both sides by -1. So that's just going to make this positive. That's going to make this positive. That would make the c be a minus c. It doesn't really make a difference because what we can do is just say, instead of saying minus c, we can just say plus some other unknown constant that we haven't determined yet. So it's okay if we kind of rename it to some other unknown constant. Then to get the z out of the exponent, what we want to do is take the natural log of both sides. So when we do that, what that's going to do is it's going to cancel, this natural log is going to cancel with the e, and we're just going to get negative z equals the natural log of e to the t plus our unknown constant that we have here. And then we can just again multiply both sides by -1, getting z equals negative natural log of e to the t plus our unknown constant, all within the natural log there. And now, since we have gotten z all by itself, we don't have an initial condition here. So we're not going to be able to solve for our unknown constant. This is just going to be our final solution here. So again, if you found this video helpful, please give it a like, hit the subscribe button, hit that bell icon so you're notified of all my new videos. That's the best way to help support my channel so that I can keep making more videos like this. Thanks, and see you next time.